And more talk about solutions. In today's lesson, we're going to talk about the nature of solutions and factors that that affect solubility of the solutes. So we talked about solubility previously as just whether or not a solute is soluble, but we can quantify that now into a look at how soluble something is. And so solubility in today's lesson is going to indicate or be indicated by the amount of a solute that can be dissolved in a given solvent. And the solvent we're usually going to work with is going to be water at a given temperature. So we're going to see a temperature dependence. And we're going to measure this solubility in the grams of solute that can be dissolved in 100 grams of solvent or 100 grams of water. But before we get to that actual quantification, let's talk about three different kinds of solutions that exist. In the first kind of solution, this is an unsaturated solution. And in an unsaturated solution, we have less solute than can be dissolved. In other words, there's more room in the solution to put more solute. So this is solvent. This should be solute can still be added. I'm sorry, that's okay. Solvent can still dissolve more solute. There's room for more solute. More can be added. And if you look down below, that's the first beaker we have here, in which we have only 150 grams of glucose. It sounds like a lot, but it's not a lot compared to how much you can put in. That glucose in 100 milliliters, which is the same as 100 grams. Remember, grams and milliliters are the same thing at 20 degrees C. So an unsaturated solution contains less solute than possible, and there's room for more. Now, let's go back up and take a look at the next line. And in the next line, we have a saturated solution. Now, saturated, you've probably heard this term before. This is kind of like a sponge where you can't put any more water into it. It's reached its limit. Think of it like that. A saturated solution we're going to define as one that contains exactly the total amount or maximum amount of solute. Excuse me. I didn't need this extra line here. That can be dissolved. I'm trying to draw an arrow. That can be dissolved at that temperature in that solvent. All right, so it's again at the same solvent. Dissolved at that temperature. It can't hold more. This is the solubility. So the solubility is now going to be defined as the amount of solute, a solution that has the maximum amount of solute it can contain. Now, we're going to get back to this a little bit, but I want to point out that if you see a solution with undissolved solute on the bottom, this solution is considered saturated. So in beaker number 2, we have a saturated solution. The saturated solution can't hold more solute. So it's the maximum solute possible. So what happens if you try to put more solute in? Many of you have probably experienced this in a restaurant when you're trying to sweeten your iced tea or sweeten your drink, and you keep pouring more and more sugar in the hopes to get that sugar dissolved. And at a certain point, that sugar ends up on the bottom of the glass, or on the bottom, in this case, on the beaker. So anytime you have undissolved solute, it's a solid in this case, that's indicative of a saturated solution. So for glucose, the saturated solution is going to be 200 grams of sucrose. I say glucose before sucrose in 100 milliliters of water. And if I try to put more in, I'm going to have that 200 grams dissolved up here. But I'm going to have that 50 grams, so it says it down over here, 50 grams sitting on the bottom, not doing anything for me. Now, there is a way to get it dissolved, and we're going to talk about this in a little bit. And this is by making a supersaturated solution. And we're going to see that on the next page. We'll see that later on. Just to let you know ahead of time, a supersaturated solution contains more than the maximum amount of solute that's possible. Now, how do you get there? There's a very special way to get there, and we'll talk about it on the next page, but you cannot be made by simply adding more solute. And if you add more solvent, well, you're putting in too much solvent now, and you're going to be able to dissolve more, but it's not going to increase the solubility. It's just going to increase the total volume of the solution, and so you're going to dissolve more of the solute in that larger volume of the solution. Concentration. We saw concentration the other day. Concentration was that molarity. But concentration, as we saw, is the actual amount of solute dissolved. And now we can talk about a concentrated versus a dilute solution in terms of the solubility limit. A concentrated solution has a large amount of solute relative to the solubility. So it's a high amount of solute relative to how much you can put in. A dilute solution has a little amount of solute relative to the solubility. So we can now think about the solubility, the concentration as basically, it's going to be different for everything depending on how much of that particular solute you can dissolve in a beaker or in a solution. Now, making a supersaturated solution, in order to get everything dissolved, as we're going to see on the next page, increasing temperature is going to increase the solubility. So the only way to make a supersaturated solution is to heat up the solution until all the solution, or all the solute, that should say solute there, all the solute dissolves. Once all that solute is dissolved, you can then slowly and carefully cool the solution down. And if it's a solution or solute that's capable of making a supersaturated solution, that solute will stay in solution. This is an unstable situation because that solute really is trying to crystallize and come out of solution, but there's reasons why it can't. And what happens is the solution contains more solute, and it retains the heat used to dissolve. This is a way of storing heat, and I'll show you a demo in a little while about this. But you can recrystallize it, and the way you can recrystallize it is to shock the system, and the demo will show you the shocking the system. Scratching the beaker. If you remember in the aspirin lab, we had to scratch the inside of the flask, and that was in order to encourage the crystal, if you will, to precipitate or to crystallize, or to use a seed crystal. So it's a small crystal of the solute, and you put that into the solution, and it gives the solute something to crystallize on. When it crystallizes, the stored heat gets released. As we reform, we make those solute bonds, And remembering for that forming bonds is always exothermic process, just like condensation or freezing were also both exothermic processes. Now we'll talk about this making a saturated solution or supersaturated solution again on the next page. So if you turn to the next page, we have a diagram, which is also chart G on your reference pack, called the solubility curves. And this is the curves for a number of different solutes for how soluble they are in 100 grams of water. So there's our grams of solute on the y-axis per 100 grams of water. And on the x-axis is the temperature going from 0 degrees Celsius to 100 degrees Celsius, because this is for liquid water. And the way you're going to read this is by finding the particular solute you're interested in and following its curve and finding where that curve intersects a particular temperature, or finding where the curve intersects a particular grams if you want to know what temperature to get to. And so you have to isolate, you have to focus only on one particular curve. So in the first question, I want to know, what is the solubility of potassium chlorate, KClO3? So let's go down and find KClO3 on our plot. And here it is. KClO3 is the line that starts here. And I'm not going to draw the whole thing, but I want to know, what is its solubility at 50 degrees C? So I come to 50 degrees Celsius and come up 50 degrees Celsius until I reach the KClO3 curve. And when I do, I can see that the intersection between that curve and 50 degrees C is just around 21 grams per 100 grams of water. And you want to say that whole thing because it's going to tell you if there's a change in the amount of water. Say if I cut that down to 50 grams of water, then I'd only be able to put in half the amount of solute. Next, I want to know, let's change colors, at what temperature does KCl now, potassium chloride, not potassium chlorate, have a solubility of 50 grams per 100 grams of water? So I'm going to come up to my 50 grams of water here, and I'm going to come over to my KCl curve. KCl is this curve right here, this KCl. So that curve intersects the 50 grams of water at, I don't know, what does it look like? About 75 degrees Celsius. Maybe you're going to say 76. By the way, reading these curves, as long as you're close, you're going to be okay, because it's very difficult to read these that precisely. So let's say 75 degrees Celsius. Okay, now we're going to get a little more complicated. Suppose I put 80 grams of potassium nitrate into 100 grams of water at 30 degrees C. So let's find that 30 degrees Celsius on the plot. There's 30 degrees Celsius. And let's come up to whichever we hit first, either the KNO3 line or the 80 gram line. So we come up, and here's KNO3. It's a really steep curve. So KNO3 is this curve right here. I didn't do a very good job drawing that line. So we hit the KNO3 curve before we hit 80 degrees. Now I'm going to 80 grams. I'm going to put a little circle up at 80 grams as well, because that's going to be important in a moment. So this is now going to be a saturated solution, because into that saturated solution, I'm going to be able to put about 47 grams dissolves. 47 grams is the saturation limit. So I have 47 grams dissolved. That means that the difference here, the difference was 80 minus 47, or now 33 grams stays undissolved, and that's how much sinks to the bottom. Okay, so about 33 grams of it sinks to the bottom. Can't dissolve at 30 degrees C, but it can be dissolved, if you notice, by taking that temperature. Sorry about that. Taking that temperature, and if I raise that temperature up at least to, what temperature is that? That looks like about 48 degrees. Increase the temperature, so greater than equal to about 48 degrees Celsius, then that 80 grams will dissolve, because 80 grams is the solubility limit. That's the solubility of KNO3 at 48 degrees C. Now, you may come up upon a solution where you haven't put the limit in. So now let's look at potassium iodide. Here's potassium iodide way up at the top of the curve. And if I can put 100 grams of potassium iodide into 100 grams of water at 20 degrees C. So here's 20 degrees C. I wish we'd stop doing that. So 20 degrees C, I'm going to come up to, now I'm going to hit 100 grams before I hit my potassium iodide. So I am below the saturation limit relative to the potassium iodide. So this is an unsaturated solution. And by subtracting the amount that I could dissolve, so the solubility limit looks like about 140, let's call it 145 grams per 100 grams. If I subtract that 145 minus 100 grams, means that I have 45 grams of solute, more room for 45 grams of solute. So 45 grams, we'll put that in here. That's how much extra I can dissolve. Now, how about that special supersaturated solution? How can I make a supersaturated solution? How am I going to indicate that on this curve? So to make the supersaturated solution, let's say that I want to dissolve, I want to have 130 grams of KNO3. So we're going to go back to our KNO3 again. And I want 130 grams of KNO3 to be, oh, I don't have it here, do I? I want 130 grams of KNO3 at, let's write that in here, KNO3 at 30 degrees C. So I want to have that supersaturated solution. So let's mark on the curve, on the plot, 130 grams at 30 degrees C. Now, there's no curve there, but remember, we're going to be dealing with the potassium nitrate curve. So here's 130 grams at 30 degrees C. Now, if I just try to put 130 grams, sorry about that, I wish we'd stop doing that, at 30 degrees C, I'm going to get stuck at the saturation limit for the KNO3. Oh, where did my point go? Oh, it didn't like that. Let's try that again. Whenever I touch the pad, it moves. That's why I hope I'm not making anybody dizzy here. I'm making myself dizzy. Let's try it here. All right. So I can only put that 47 grams dissolved. So what I'm going to do then is I'm going to heat the solution up. Now, in practice, we usually put the solution into a boiling water bath to make sure that it gets heated up properly. But I know that if I get the solution heated up now to at least 69, 70 degrees, then I'm going to reach my saturation limit. And then here is what we're going to say. So we're at our saturation limit. Everything has been dissolved. Once we get everything dissolved, I'm sorry about that, we're going to slowly cool it. So I'm drawing this dotted line coming back to 130 grams at 30 degrees C. And if I've done this properly, I should have a supersaturated solution. So you heat it up to a high temperature and you cool it slowly and carefully. And on the previous page, we talked about things to make it crystallize, a seed crystal or shocking the system. And what I'd like you to do is pause the video right now and go look at the supersaturated solution video that's also attached to here, in which I'm going to show you some sodium acetate hot packs. These are reusable hot packs. They're not as good as the newer versions of the hot packs that, say, skiers or people who are out on a cold day would use. But they work. They do heat up, and I'm sorry. I wish you could feel how hot they were, but unfortunately, that's not going to be possible. Okay, so I hope you went and watched the video. If not, make sure you go do that. And let's finish this up by talking about the temperature dependence of the solute. Now, if you look at most of these solutes, most of these curves, as the temperature increases, the solubility increases. And those that you're looking at that happens are solids. And so, actually, let's change colors. What color should we use? What color haven't I used yet? Go to red. So the solubility of most solids will increase as the temperature increases. And you can see that for practically everything. Even sodium chloride does have a slight increase in solubility as the temperature increases. But there are three solutes that you have on this chart whose solubility decreases as the temperature increases. And what are those three? We see SO2, we see NH3, and we see HCl. Now, everything else on here is a solid. And although we don't have any, it looks like all ionic, so we don't have any covalence. This is going to work even for covalent solids. I'm not sure why they don't have covalent solids on this chart. But gases go the other way. Gas solubility decreases as the temperature increases. And part of the reason for this is that the liquid basically is bumping, I'm not writing very, bumps the gas out of solution. There it is right here. Higher kinetic energy, the solvent molecules bump the gas solute out of solution. And you've seen this, in effect, when you see soda that goes flat. It goes flat faster on a hot day. So the temperature dependence of gases is the opposite for that of most solids. Now, I do say most solids because there are some occasional solids that go the other way, and I'm not going to get into explaining those either at this point. Henry's law is basically like the gas laws. It's a statement of how the solubility of a gas changes with a function of pressure. So the solubility of gas, we're going to call that solubility S. This is really, the solubility of a gas is really its concentration, because with a gas, the gas is always going to go to its maximum solubility. That maximum solubility depends on the pressure. And so this is directly proportional. Remember what that means. Directly proportional to the pressure of the gas. So as the pressure of the gas increases, its solubility is also increases. What happens at higher pressure? At higher pressure, there's more collisions of the gas molecules with the liquid. Remember, as you increase the pressure of a gas, you get more collisions. So instead of having 2 collisions here, we got 1, 2, 3, 4 collisions. Double the pressure, you double the number of collisions. Well, if you double the number of collisions, you're going to double the amount of gas that's going to make its way into the solution. Now, we do have the gas molecules coming out as well. And so this is in the kind of equilibrium that we saw before with the vapor pressure. But this equilibrium has to do with the amount of gas that's dissolved. So I'll talk about this in a moment when we talk about soda can opening or soda bottle opening. So at a constant temperature, so now we're going to limit temperature, the direct relationship tells us that the solubility at one pressure divided by that pressure is equal to the solubility, the same ratio, solubility at the second solubility at the second pressure. And sometimes we even come up with a constant for it. And in the homework, you'll have one question in which you're going to come up with this constant. And the constant can depend on how you measure your solubility. So one of the ways we're going to measure the solubility is in terms of the grams of gas that can be dissolved in a liter. So I want to know what's the solubility of a gas at 12.8 atmospheres. So this is going to be my P2. If its solubility at P1 is 1.40 atmospheres, S1, not S2. S1 is going to be 0.480 grams per liter. Let's set up that equation. S1 over P1 is equal to S2 over P2. I'm trying to solve for S2. So rearrange, and S2 is equal to S1 times P2 over P1. So notice as the pressure goes higher, the solubility is going to go higher. Now let's plug in our numbers. We have 1.40, solubility, not the pressure, 0.480 grams per liter times 12.8 liters, 12.8 atmospheres. Divide that by 1.40 atmospheres. We're keeping sig figs good. Let's cancel out the atmospheres and do the math, and we should get that S2 is equal to 4.39 grams per liter, and that S2 did go up as the pressure 2 went up. The opposite happens when you open a soda bottle. So for a soda bottle, the pressure of the CO2 is about 5.0 atmospheres. It's pretty heavy, pretty high concentration or pressure of the soda bottle. And all the CO2 is dissolved. When you open the can, the pressure of the CO2 drops. And it's not just down to 1 atmosphere. The pressure of the CO2 is like 1/100th of an atmosphere. Really, really low. And so if the pressure drops, the solubility goes down. Because the solubility goes down, these are the bubbles that form. The bubbles that form. And these are the same bubbles that happen if a scuba diver would come up too quickly. As the pressure goes down in their lungs, the nitrogen will come out of solution if you don't get rid of it very quickly. As I said, there is an equilibrium, And what the scuba diver has to do is come up to the surface slowly to allow that equilibrium to take place and allow the nitrogen to come out of his or her bloodstream. Okay, so this is the different factors that affect solubility, and using those solubility curves, the homework will involve looking at those solubility curves and doing some calculations with the solubility curves with Henry's law and describing the kind of solution that you have, saturated, unsaturated, or supersaturated. I will see you next time in class, and I hope you're doing well.